Okay, yeah, so today I see that we have many different materials, and today I titled our contribution from design modules to lasers. What we have now learned, yes, is that there are many different photonic integrated circuit technologies, right? So last year I talked to someone coming from the EDA software, so really from the electronics part. He said, I'm looking at the photonics landscape and it looks a little bit like Wild West to me, because you have many different platforms and we've learned that they have really great advantages, right? For example, aluminum oxide bringing amplifiers on the menu card, or lithium niobate or BTO, really enabling high-speed modulators that are, for example, not reachable by silicon insulator easily. But in order to give people an overview, we indeed on our website made a mini PIC guide where you can look up the different material platforms, and their typical application areas, and some downsides and upsides. So if we look here, for example, in the spectral ranges, they really differ a lot. Going from down to 200 nanometers up to into the mid-infrared. But if we look at all these different material platforms, and I think all of them were mentioned during this meeting, that most of them need laser technologies integrated. I mean, Hamad said it for Seacraft and lithium niobate, that's on their roadmap. But you see that except indium phosphide, all of them lack lasing materials. So this will be integrated at some point. So we see that we have a very fractalized supply chain. We have many different technologies. We also have many different packaging methods, but we also have many different EDA solutions, which, for example, small foundries with novel materials want to be reachable by many customers, and they don't want to stick to a specific EDA solution to do their designs. So that's where we also help. We help customers in the planning and design. We can also support fabrication and testing. So we have a broad supply chain. But also we do help people mentioning PDKs, or helping people putting PDKs out there. And typically, if we talk about PDKs, there are many different ways to look at it. Many people see that it's sort of the Lego blocks that we put together, but that's only the upper level. It basically is an enabler for foundries to map their technology into software. And there we have profound EDA software expertise, which we help with a standardized way of writing this up. Then you can convert it and look out to and export it to different software for EDA solutions. For example, commercial vendors like Synopsys and Lucida is where we're working closely together for XPDK development, but also on the same hand on open source. For example, you want people to use the open source software that is available there if they don't want to, at this point, spend their money on other design software. And this basis on PDK is also for us the basis for EDA solutions. So what we have a design module philosophy. That means that above the PDK we put an extra abstraction layers. So because the question arises, if we have so many different technologies, how actually do we transfer designs from one platform to another? So what we do on our side, we also enrich the PDKs on our side and remap the building blocks such that you can have very more complex building blocks that you can easily transfer between the different technologies. It could be as simple as an MZI or modulator, but we also are doing this with more complex functions. For example, filters or switches. Think about, for example, lattice filters, where you really want to have specific filtering for wavelengths or other applications. Or what we're currently also commercialize or have other people evaluate is the hybrid lasers, where we have an external gain section, because we've seen that most of the technologies lack active lasing and will need some laser integration. So what we've done is we made a hybrid laser design module that can easily map on different technology. And we're currently in the phase of testing these out and really validating them. So we have it available for silicon photonics, on silicon nitride. Aluminum oxide is something that we are actually looking at also in a project together with Alluvia, but also lithium niobate is very, very, very interesting for let's say the next generation of coherent communication, for example. And on the other hand, we also have matching to our design module for your foundry, your technology that you choose. We'll also have laser chiplets already available, such that you can make one run at the foundry and just take off the stock, off the shelf gain sections that match with it to do validation. And on the other hand, what we'll also have available soon, currently in production, are evaluation modules. So you might be interested in the hybrid lasers we provide that you can put on your designs, but first you want to test it. You want to test it. Does it work with my system? Is it reliable? Does it suit you? And then we can supply you already evaluation modules that you know that the design you put on your wafer run works for you. And with that, why can we do it? What we do? Because we are a service company mainly, but we have decades of experience going back with our CTO into the early 90s, which already did his first designs and commercialization of integrated photonics technologies before the .com. And with that, I would invite you to have a look at our website, have a look at our mini guide. If you have additions, let us know. Then we are happy to include more technologies or also talk with you about it. Other than that, I would like to thank you for your attention, and I'm happy to take any questions. Otherwise, I think it was a great meeting. Thank you.